DINOv2, which you've probably heard about, is a self-supervised model created by Meta. It's a very powerful model. It's winning a lot of benchmark competitions. It does depth estimation, image segmentation based off of these latent space representations that are self-learned. I've been studying this model for about a year now, and I condensed everything I've learned so far into a kind of visual understanding so that you can quickly understand exactly what's going on. And then I've also adapted code that's kind of concise and kind of to the point about what's exactly going on within the model. But first I want to lay some groundwork about what's happening. So if you imagine you have a classifier that just classifies dogs or cats, you could paste a dog image through this model and you get a softmax probability of it being a dog or a cat. And if you remove that classification head, those red nodes there, you just will have a model that creates a latent space representation. And if you add a decoder onto that, and the reason I want to kind of explain this is that latent space is kind of an important kind of topic for the Dino model. But this would be a VAE, a representation of it. You pass a dog image through, you get values within the center that are a latent space, and the decoder tries to reconstruct that same image. So that's a self-supervised model. A VAE is a little bit different, it's a little bit older. But the idea is that you have this kind of constructed latent space that is kind of has knowledge of the images that you pass through it. And if you make changes to it, it changes the output. So this is an intelligent, kind of compressed version of what the images that are passed through it. And it's kind of organized, and it has an idea about the differences and the variations that pass through this type of encoder. And on the other side, if you just take the encoder instead of the decoder, you pass images through. And since I chose 3 values, that latent space will look like a 3-dimensional kind of space. So it's just easy to see. Typically this space is much larger, but it's the same idea. But you pass these images through, and what happens, similar images get put in similar areas within the latent space. And if you walk along this latent space, you should be able to get mixes between. So if you chose a point between these sets of images, it should be a mix of a dog and a cat in some sort of intelligent way. And if you move in any direction, you get that different variation. Now the Dino encoder takes a little bit different approach where it uses a vision transformer and it wraps that. So the Dino model is actually just a wrapper around a vision transformer. And then a vision transformer just takes an image, divides it into patches, passes it through. You get that softmax classification if you have that MLP head. But you take that classification token there on the end, and that's what actually goes through the MLP head. But the Dino model passes it through a Dino head, which is just a little bit different, but it's really not that complex. So the Dino model is more about a change in kind of the training, and it's kind of a clever training and a clever augmentation to kind of get a self-supervised approach. So here's a representation of the augmentation. You get 2 global crops and you get local crops. So local crops have more of a zoomed in, kind of more localized features, and the global crops have more global information. A teacher and a student are the copies of the same thing, but the teacher only gets the global images. The student gets the global and the local images. And then you're able to self-supervise, meaning that you're trying to reduce the distance between the output of the teacher and the output of the student. And by doing that, you're kind of saying that these images are the same. Find out what's kind of same about them without having to get any labels onto it or anything like that. And it's kind of reducing the space. Now that image is a little bit wrong because the Dino does something a little bit different than just encoding to a space kind of like a VAE. What it does is it takes the outputs, which are kind of like that latent space. It's the embedding token. For the teacher, it centers it, meaning it subtracts its own mean from previous batches, this sort of thing, and it centers it around 0. So you don't get these values that are really far out. It regularizes it. But then you apply a temperature softmax. Usually softmax is used for classification. But they use this in a kind of interesting sort of way. If you look up at the top, you get a typical output of a softmax. But if you add temperature to it, it regularizes it, and you don't have these extreme differences in predictions. The higher the temperature, the less kind of differences you have. And then the Dino model has 65,000 of these. So as if you had 65,000 of these classes, and it compares those teacher outputs to the student outputs. Now the teacher outputs are regularized, and then you do a binary, or sorry, not a binary, but you do cross entropy between the two, and that's actually what gives you your loss. So it's kind of this kind of augmented latent space is kind of what's giving you this kind of output. But you also do something a little bit different as well. At each update step, the student is actually the only thing that learns. The teacher is just a copy of the student. So after the student learns what it needs to update, it updates itself. And then the teacher is an exponential moving average of the student. An exponential moving average is something that you'll see in finance. So to get that kind of idea of what's actually going on, here's kind of a plot of kind of what an exponential moving average would be to a trend. And then if you look up there in the kind of values there, that's the alpha values. As the alpha value increases, the trend fits tighter and tighter to it. So the teacher is the same thing as the student, but you have this kind of regularized version. You're taking the parameters that are updated through the student and applying this exponential moving average. So the teacher is in all ways a regularized version of the student. You're regularizing the teacher by centering it. You're regularizing the teacher by applying this exponential moving average. And then you're also doing a kind of regularization by only passing global crops through it, where the student is built around exploration. And I'll kind of show this how it's reflected in the code as well. So we can go to the code and look at that. Okay, so here's an example of the code I have. First, we'll talk about the data augmentation, the Dino model, training methods, so you can actually train your own Dino model from scratch. And then a demonstration of the model. And then I also have some pre-trained models. Here are the publications for the two papers that came out around Dino. The first one kind of just talks about the general idea of the training loop process that we talked about before. And then V2 has, robust kind of version of it. It has a lot of stuff for like distributed computing, this sort of like optimization, this sort of thing. But data augmentation, we talked about that before. We can wait for this to start over, where you have just an image that passes through. It has variations of global crops, and then you keep doing that, and you do as many local crops as you have set. I think they have like 8 local crops set as the default, but these contain most of the information, the global crops, and then local crops are more fine-grained information. And the teacher model only gets the global crops, while the student model gets both the global and the local crops. But the student and the teacher aren't compared if the same images pass through it. So I can show you where that's at in the code. I have some text that kind of goes through everything, but here's the main thing. Seeding, I just make sure that all the seeds match so that you get the same outputs that I do. I'm loading a version of the data set that uses ImageNet. ImageNet is what they talked about using on the paper that they published. So that's what I used as well here. So this is a data loader. Although my ImageNet version is images that are 64 by 64. I have a sample that you can use, but you can use a larger size. It's easy as well. This is the main thing, the Dino augmentation. And that's where kind of all this code is at. This is kind of the ugly side of self-supervision in quotation marks, because these values you set here, these will determine a lot about how well the model performs, and these are very data set specific values. And what I can mean by that is if we look back up here and you have these global and local crop things that we talked about before, if your local crop is too fine, like maybe it just zooms in on only the tooth, that's obviously not going to get a good connection between the large image and the small image. So it's very data specific, and these values would work differently with different models, especially these random cropping values. So different data sets would probably require different croppings to be able to kind of get this self-supervision you need. So this is kind of the ugly side of the, in quotation marks, self-supervision. This needs to be adapted or changed or researched a little bit more to do this a little bit more intelligently. And something that could be done that allows you to have these values that generalize to all images, which is probably not the case for what we have now. And then if you open that up, then you could have that kind of large language model effect. But that's just a little 2 cents there. But this is global crop, local crop. You can see the local crop just has options that are more fine-grained. You can see the scales, this sort of thing. Number of local crops, I have it set to 4. I think the traditional is 8. If you load the data set, we can just look at what the data set looks like. So this would be taking one image of our 64 by 64 images. This would be the the second global crop, or the first global crop, second global crop, and these are the fine grain crops or local crops. And you see it has very specific information about the images. And then we can talk about the Dino model, what's kind of going on exactly in here. So here's where the Dino loss is kind of initiated, and the Dino class, which has the Dino head in it. So the Dino loss, this is the part where it loops through, like we talked about before. It skips over if the global crop that's passed through the teacher is the same as the global crop that's passed through the student, and then everything else gets that log of the student's output, and then just the teacher's output, and you do the sum, and that's the loss. It's pretty simple, nothing too complex there. Let's see. This is centering. This is what we talked about before, where you center the teacher but not the student. You can see the teacher outputs get centered this way. The Dino model is here. You have the Dino head, which you just have the embedding and then the output, and then whether you use batch norm. But the Dino head is very simple. Nothing crazy here. So you can see that you get the sequential of just the teacher model, which is the Dino instant, which is just vision transformers that you choose. And then the output of the vision transformer gets passed to the Dino head. And that is the same for the teacher as it is for the student. Simple. Let's see. I have this method here. They use get last attention, so you can look at the attention output of the teacher or the student. And the interesting thing is, when in inference, you can use the outputs of the teacher or the student, and the teacher or the students have different characteristics after you finish training, and different ones are better for or more suited for different tasks. Generally, I think the teacher is kind of maybe a little bit better actually, but I think that's just in general. add-ons, if you don't know, this has some sort of weight decay. So if you have really large weights, add-ons, in my experience, almost always outperforms atom, especially the case with large language models, or of course large language, but I meant large models with like some sort of deep network. The add-ons with the weighted decay almost always works better. Okay, so you initiate your Dino loss. Simple stuff there. Here's your training loop. You get, this is your unaugmented images. These are your augmented images. They get passed through the teacher and the student, except the teacher only gets the global crops. The student gets all of them. And then you compare those losses, but you only, you never compare something that matches that's been passed through the student to something that matches that's been passed through the teacher. And then you sum those, and that gives you your output lost. Obviously, you have a backward step and then an optimization or optimizer step. I have where you save the weights here. Pretty simple stuff. Nothing seems to be of too much interest here. This is where you apply the exponential moving average. This is your momentum value. And I have another notebook that we'll talk about, but this is your momentum or alpha value. This is a very high value, means that it's going to be very close to what the student model is. It's just going to shave off those really, really extreme values during your update of these parameters. Okay. This is if you want to load the model after you've trained it. You can load the model and get some predictions out. So this is what it's attending to. These are the heat maps of the attention head. This is the overlay, obviously. These are different heads. So this is one head here that seems to attend. This is kind of a weird image, but it attends a lot to this box. You can see that. And then it kind of ignores the background. And you see the different things that it attends to on the box as well. And then you can see this other head has different attention maps. I also have where you can load a pre-trained model. So you can specify which Dino it is. It loads from this hub, which just loads the pre-trained Dino model. And then I have how you can use it. So if you just pass your image here, I have loading this image here. You just change this to the path of your image, and you get some output there. This would be your attention map. You can look at what that is, but if you want to actually visualize the attention map overlaid on the image, you can pass it through this thing I have here, which is visualize attention. This wasn't in the Dino code. Actually all of this code that's in this notebook isn't in the actual Dino repo. It's all kind of my wrapper functions. But I'll show you what this does. This is the overlay of the attention. So you just pass this image through the Dino model, and you look at all the different heads, and you see what they're attending to. And you can see they attend to all different things. Some attend to the shoes, some attend to the phone, the hands, some attend to this kind of menu back here. But you can see kind of what all it looks at and different things that it ignores. One who attends to the plant. But it's very interesting seeing kind of what's the output here and how this kind of works. But in general, like I talked about before, the Dino model is going to kind of, in effect, be a large language model version of Vision. So it's where you can dump just every image that you've seen online and have a model become generally functional, which is what we've seen with large language models, is if you just keep dumping data onto a model, it gets kind of like really seemingly intelligent, gets really good outputs. So if we open this up to this self-supervised Dino kind of approach, we're getting in the area where we can just dump all these images, all these videos that we have access to online, and learn something from them, which is probably something that are learned, which is kind of if you think about large language models, that they can just take any text, predict the next word, so this is kind of something like that. And I think this is kind of the direction of all these vision models are going to have something like this, where you're using the weights of these large language models as kind of part of your vision model. So you're going to have these pre-trained models kind of feed into your models. Probably this one and that segment everything model, these sort of things kind of all feed into a model that will actually give you some predictions. I think that's the future of this sort of thing. I also have some other things as well here. So if we look at this miscellaneous file, I have some explanation here. This is the actual Dino loss. They have a version of this in the paper, but I explain kind of exactly what it does. I put it into Python code. Very simple. You're taking the output of the teacher and the student, which is that classification key from the vision transformer of the student and the teacher model. And then this would be the output passed to the Dino head. And then what you're doing is you're applying a softmax to the student with temperature, which temperature means you divide by some value. And then you have a softmax of the teacher, but then you have centering. The center value comes from previous epochs. You're going to center around 0. So you're going to have to try to make your teacher output have a mean of 0. And then you're just doing a cross entropy loss between your softmax of your teacher and your student. And this kind of makes that latent space a little bit different, a little bit more concise. Works a little bit better. This just shows the log curve. So what you're doing is you're taking your values that are output for your probabilities, and you're doing a log of those, so you get these values, and then you're multiplying that by your teacher's outputs, and that gives you your loss. This is an explanation of the exponential moving average. So your alpha value is that exponential moving average value. For the Dino model is that, I think it's 996 or something like that, very high. But this kind of shows you how I generated that graph, and it actually has the GIF here, where you keep increasing the alpha and it fits really tight to the data. And their alpha value is so large here. But you can kind of see kind of how it works as you increase the alpha value, how it fits more and more. And then also how it leaves out like this mean here. It doesn't get all the way there, even higher ups. And it doesn't kind of have all these kind of variations with the data. It just kind of centers around the mean without having these extreme outliers, which helps regularize the teacher. And this is what it's kind of all about. I hope that makes sense. I have all this posted on my GitHub. So if you just go to my GitHub, you can see these values are kind of reflected, or these files are reflected here. So if you found this interesting, leave a comment about kind of a model that you would like to see. This is kind of my traditional method. When I first get a model, I have to go through and kind of make it more concise. So I think since I already do that, I'm just going to go ahead and keep posting these so that you guys can kind of benefit from that as well. I do a lot of research, so I'm always kind of covering different versions of these models. But like the video and star the repo if you found it interesting.